So in the introductory module sessions, we saw a little bit about the entity relationship diagram. We saw the meaning of entity sets and relationship sets. We went through the overall database design phases in 6 stages, right from the requirements analysis phase to the user interface design and the security design phases. We also looked at the different types of data models. So in the next few sessions, we look at the entity relationship modeling in detail. So the objective of these sessions would be to be able to effectively conceptualize the database requirements of a client given the specifications. So after the end of the module on the design using the entity relationship model, visit the objective and see if you have been able to effectively conceptualize the database requirements and come up with a ER diagram that suits the enterprise. There are sub-objectives, which is basically knowing which ERD concept is to be applicable at that point of time. We'll see how we can capture some ICs using mapping cardinalities, but not all ICs that are integrity constraints can be captured in an entity relationship diagram. So we will see which of these ICs or integrity constraints cannot be captured also. We will be drawing the entity relationship diagram using the Shen's notation. So you should be familiar with the Shen's notation by the end of this sessions. Okay. We would need to borrow some concepts from the extended entity relationship diagram to be able to capture some of the specifications which cannot be captured originally in the ERDs. Okay. And then finally, we will transform the extended entity relationship diagram in an optimal manner to normalized tables. So we'll look at what normalization is all about, and then we will see how to translate this into normalized tables. By default, if you've drawn a very good entity relationship diagram, you would end up getting your tables automatically in third normal form. Okay, we will also visit the object relational database management concepts in the conceptual design phase itself. Okay, so that was the extension that we saw, which was needed. The extension actually originated first in the SQL and C standards, and then the ER diagramming needed to capture these extensions also. So then the ER modeling diagrams also started changing. Okay. So to recap, actually, we did see the entity sets, the relationship sets earlier on, but we will go through this again in brief this time. Okay. So the entity relationship, or the ER data model for short, was developed basically to facilitate the database designers by allowing the specification of a business or an enterprise to facilitate you to create the schema for a business or an enterprise. And that would represent the overall logical structure of the database. The ER model is very useful in mapping objects and the interactions of these between these objects in a real world enterprise into a conceptual schema. Okay, so we saw what entity sets are. So just a revisit of that. An entity is a thing or an object in the real world that is distinguishable from all other objects. For example, we captured entities like the student, the instructor, the course, the classes, the classroom, okay, when we looked at the university database organization as an organization in our previous slides, okay. If you realize we did not capture the university as an object or as an entity, the reason for this is because we were actually describing a particular university, okay, so it was an intrinsic entity within the ERD itself. So we didn't need to capture it because we were designing it for a particular university. If we were designing a general application for all the universities that were there, then we would need to capture the university also as an entity, and it would have attributes like university identification, the ID for that, the name of the university, the location of the university, and whatever other kind of attributes we would need to capture. But in that particular instance, we did not capture it because it did not, we were looking at one single university and the information regarding that single university. Okay, so an entity has a set of properties And the values for some set of properties may uniquely identify an entity. For example, you are given a unique student ID with a value that uniquely identifies you. You know that your name uniquely identifies you, but when we're looking at a situation where we can have uh, all of you in the database and some of you may have the same name by chance, we need to somehow uniquely identify you. So for that, you're given a unique student identification. Okay. An entity may be concrete, such as a person or a book, or it may be abstract, such as a course, okay, or a course offering. So in the again, going back to the university example, we saw that classroom was concrete, but classes were an abstract entity. Okay. So an entity set is a set of entities of the same type that share the same properties or attributes. So the set of all people who are instructors at a given university can be defined as the entity set instructor, or the set of all students would be defined as the entity set students. Okay. Entity sets need not be disjoint. Okay, we also saw these in our example previously. So an entity set need not be disjoint. So we had an example. We said the customer could be a customer and employees of a bank. The employees could be customers of the bank also, right? So that is a non-disjoint entity set. But if you're looking at the banking example again, and you're looking at the loan as an entity and the account as an entity, then loan would have a unique identification and account would have a unique identification also. And the loan and the account are going to be disjoint by default. Okay. So we have disjoint and non-disjoint entities. Okay. An entity is represented by a set of attributes. We saw that, right? Attributes are descriptive properties possessed by each member of an entity set. Okay. So here we have an employee information, employee entity with attributes social security number, name, and lot. Okay. The social security number is the identifier or the unique identification for the employee set. So each social security number, a unique one, would identify the entire tuple or the entire record within that particular database for that particular employee. Okay. You can think of these attributes right now as fields in a record, and you can think of the tuple as a record. Okay. So all entities in an entity set have the same set of attributes. Each entity set has a key or a unique identifier. Okay. Each attribute that we looked at, we saw needs to have a domain from which it comes back. Okay, comes from. So each entity has a value which is atomic for each of its attributes. For now, we look at the fact that every value should be a single value. Okay, that means it should have only one value. You cannot have a set of values kept within that particular attribute. A database would now include a collection of entity sets, each of which contains any number of entities of the same type. Okay, so that's how you view a database, as a collection of entity sets. Okay. So if you're looking at this also, we see two things. We say the instructor, which is an extension. We see the extension of the instructor table or the instructor entity, and the extension of the student entity. What do we mean by extension over here? The instance at that particular point of time. So the set of records or the set of tuples in the database at that point of time. So for the instructor, the extension is all these tuples or all these records. Okay. And the intention of the schema has only two attributes over here, the instructor ID and the instructor name. Similarly, for the student, this is the extension, that is all the records within the database at that point of time for the student table and the student entity. And the attributes over here are student ID, student names. The schema consists of only 2 attributes over here. So the intention is this, the extension is this, or the intention is the schema and the extension is the instance. Okay, so that's what we need to identify these terms, okay, or know what these terms mean. We've seen the attributes and we've seen what they are. We've also seen that certain attributes would comprise a certain set of attribute, or a certain set of attributes would uniquely identify a particular tuple. Okay. Take, for example, why I said a set of attributes. So far, we've only seen that student identification could be your key, or could be the attributes that uniquely identify you. Okay. But let's go one step further and say, in a particular semester, you have a unique name in that semester, but across semesters, you could have 2 people having the same name. That means in, or let's go one step further. And so semester will be a year. So let's say when you join the university, in your class, you have a unique name. But if we look at students from one class as opposed to students from another class, somebody else in the next class could have the same name as you. Okay. So looking at this, we can have the student name together with the year he joined in could be uniquely identifying that particular entity within that entity set, students. Okay. So that's why a set of attributes could uniquely identify the record. So student. So student name and the year could be one key or one identity, unique identity. And the second one could be your student identification number. Okay. We also saw various attribute types like simple and composite attributes, single valued and multi-valued attributes, null attributes. We saw all of these. But when we say null attributes, take, for example, the phone number of a student. While entering the data, supposing we don't have it at that point of time, we enter a null value. But that null value could imply that either the student data was unknown at that point of time. That means we didn't know the phone number at that point of time, even though the student had a phone. Or it could also mean the fact that the student does not have the phone at all, right? So null values tend to create a little bit of an issue into our database also, okay? And we will see all this later. We also saw derived attributes, and we said something like age was a derived attribute, but date of birth is not a derived attribute, right? So we would rather store the date of birth rather than age. But if it was a department and we wanted to keep track of the total number of employees in that department, then we could calculate the total number of employees from the employee table that tells us which department that employee was in, right? So that would be a derived attribute, which we would like to store in our database, because computation of total number of employees on the fly would be a little bit time consuming, right? So certain derived attributes we would like to store in our database. So let's look at the representation of this. So we always underline the identity or the key, okay? A composite attribute is stored this way. So the name is a composite attribute that contains your first name, middle, initial, last name. Similarly, address is your composite attribute, which consists of street, city, state, and zip. And this itself is again a composite attribute, right? So we would store all these values in the database, okay? We also just saw that an attribute should have an atomic value, that is a single value. But here we are saying we can have multi-valued attributes for phone number. Let's say you have more than one phone and we want to capture all the information about the phone, okay? Now, this was available to you once SQL standards imported or used the object relational ideas, okay? So whenever the SQL standard was extended to contain your object relational information, we could store a set of values in a particular attribute, Okay, so this implies we have a set of values or multi-values. Okay, and we store this, which is your derived attribute. Okay, so we can store it in this fashion. So this is with respect to the attributes of an entity. We also looked at relationship sets and what they mean. Okay, so a relationship is an association among several entities. Okay, so for example, we have a relationship called advisor between the entity set student and the entity set instructor. So if we look at this particular value, we interpret this statement, that is 44553, 22222 belongs to advisor, as saying that the entity set student with this identification has an advisor with this identification from instructor. So in other words, we say Peltier is being advised by Einstein. Okay. Or if we had flipped the relationship, that is first 222 and 44553, we would have said Einstein advises Peltier. Okay. So a relationship set looked at mathematically, so is a set of relationships of the same type. Okay. So it is a mathematical relation on more than two possibly non-distinct entity sets. Okay. Because sometimes we could have the relationship between a disjoint entity sets also, and we can have the relationship between non-disjoint entity sets. So we are saying possibly non-distinct entity sets. Okay. So if E1, E2, En are entity sets, then we look at this relationship R, okay, is a subset of these particular values, where E1 is the value coming from entity set capital E1, E2 is a value coming from entity set capital E2, and so on. Okay, so that's what we looked at over here. So we said E1 comes from the entity set student and E2 comes from the entity set instructor. Okay. The association between entity sets is referred to as a participation. That is, the entity sets capital E1, E2 up to En participate in a relationship set. Okay. Now, if we come to this, we say instructor and student participate in the relationship set advisor. Okay. Now, there are also terms like that they participate as 1:1, 1:many, and so on, which we will look at when we are drawing the ER diagram. But coming to this, we know that cats, we can see two lines coming out from cat. It implies that cats is related to student in via more than one record or more than one tuple. I'll start using the word tuple now instead of record, because in tables we store it as tuples. Okay. So cats is linked to Shankar as well as he's linked to Zhang. So cats is the advisor of Shankar and the advisor of Zhang. Okay. So that means this relationship could be 1:many from instructor to student. Okay. So we will see all this thing. It may be a little confusing now, but we will see it later. Now, the function that an entity plays in a relationship is called the entity's role in that relationship. Since entity sets participating in a relationship set are generally distinct, roles are implicit and are not usually specified. Okay. But roles are useful when the meaning of a relationship needs clarification. Okay. This tends to happen when the entity sets of a relationship set are not distinct. Take, for example, an employee manages another employee. So the relationship set comes from the employee table itself. So it is a non-distinct table. So we need to specify who is the manager of whom. Okay. So if we have, in this particular case, if we have E1 and E2 standing for employee and the manager, and we say the first one is the employee, and the second one is the manager, we have to keep the role over here. Okay. So when we draw the ER diagram, it stems from the fact that this is your employee. Okay. This is your relationship that we're looking at, and it becomes a recursive relationship. Okay. So we say, now here we get confused, right? Although we have this as managers, okay, I'm writing short forms, but here I need to know who plays the role of what. So I will say this is the employee, okay, and this is your manager. Okay, so I need these roles. So this becomes your manager and this becomes your employee. Or I say managers and managee. Okay, so this becomes your manager and this becomes your managee. Okay, so I'll say MGE. Okay, so this is the need of roles when we have recursive relationships. We will look at all this in detail in the next sessions or next couple of sessions. Okay.